Hi and welcome to this video where I'm going to show you how to combine the information you receive from all three spectra, mass spec, NMR and IR, to help determine the structure of a molecule. This is the final requirement for achievement of the NCEA Level 3 standard that I've been talking about in this series of videos. So, the process that I follow, the way I do it, is to start by looking at the mass spectrum. The mass spectrum, the molecular ion peak in particular, helps you to find, tells you what the molar mass is, and if you've got an odd number, tells you if you've got nitrogen present. The presence of isotope peaks also tells you if you've got chlorine or bromine present. Then I look at the NMR, and the NMR then tells me how many carbon environments I've got and what type of things are present. I'm going to look at the IR spectrum, and that's going to tell me what functional groups I've got. Then, with the molar mass, how many carbon environments, and a few other bits and pieces, then I should be able to figure out the molecular formula for the molecule. From that, I can then draw some possible isomers which have those functional groups, carbon environments, etc. And finally, I'm going to use the mass spec to figure out which isomer it must be. Now, just in terms of grading for a sec, if you complete steps 1, 2, and 3, then that is what is required effectively for achieved. If you complete steps 4 and 5, then that will get you pretty much to a merit point. Step 6, identifying the correct molecule and providing a decent explanation. That's what we're looking for excellence. Okay, so how does this actually work? Well, let's start off. We've got here the three spectra for our unknown molecule. Now, looking at them as a whole is a bit intimidating because all I can see is lines and wiggles and stuff. So let's break it down bit by bit. So first off, we're going to look at the mass spectrum. Here it is. We're going to find the molecular ion peak. That is the one that is got the highest mass. Okay, you might see this little peak down here, right near the end of the spectrum. And you can actually count along that scale and work out that that peak is at 88. The other peak that is important is the tallest one, which sometimes is the highest mass, but usually not. And again, I'm going to count along 41, 42, 43. Okay, so that's known as the base peak, is a tall one. Now, if we look at the molecular ion, it's 88, which is an even number, so there can't be any nitrogen present. There's no isotope ratios, so there's probably no chlorine or bromine. Okay, so we have several pieces of information here already. Then we can look at the NMR. Okay, so if I look at the NMR, I've got 1, 2, 3, 4 peaks. So that's great. That means there must be 4 carbon environments in my molecule. With 4 carbon environments in my molecule, that's a good starting point. And then I look at where those peaks are sitting. So I've got one here at 170-ish, one at about 60, one at about 20, and one at about 15. So the peaks at 15 and 20 are likely to relate to CH2 or CH3 groups. The peak at 60 ppm is going to relate to a carbon bonded to an oxygen. And the peak at 170 is likely to relate to a double bonded oxygen in an carboxylic acid, an acyl chloride, an ester, or an amide. Now, you remember you get a data table which has all this information, well, has all the relevant bits on there, so you don't need to memorize exactly what things are happening at what points. Okay, so what I know right now is quite a bit of information. I've got 4 carbon atoms, molar mass of 88, no nitrogen, no chlorine, no bromine, and 2 carbons that are connected to oxygens. One with a double bond and one with a single bond. Okay, so now I'm going to look at my IR spectrum. Now remember, we're not really looking at anything less than about 1500 wave numbers because that is where we get into the fingerprint region, which is quite particular. But if we look at the top, we're going to start at the left-hand side And around about 3,000 to 3,500, there's nothing there. That means that there's no nitrogen-hydrogen bonds and no oxygen-hydrogen bonds, because that's where we find them. So amines, amides, carboxylic acids, and alcohols, all missing. We've got a nice peak here at about 3,000, so that's carbon, hydrogen. We'd expect to see that everywhere. And down here we have, at about 1750, we've got a nice strong peak, which is probably from a carbonyl group, so C double bond O. So we've got these pieces of information, okay? So now we can start putting these all together. What do we figure out from all of this stuff? Well, okay, we know our molar mass is 88 grams per mole. We don't have chlorine or bromine, so there's no haloalkane or acyl chloride. There's no nitrogen or NH bond, so it's not an amine or an amide. It's not an aldehyde or ketone because the peak's at the wrong place in the NMR. It's not an alcohol or a carboxylic acid because there's no OH stretch in the IR. And therefore, what we really have left through process of elimination to a large extent is actually an ester. Okay, we know it's going to have oxygens, and from the molar mass and knowing all this stuff, we can go, okay, well the molecular formula must have 4 carbons, 8 hydrogens and 2 oxygens. That's going to add up nicely to 88. And it's going to meet all the requirements of the things we've seen in our spectra so far. Okay, so now let's figure out what are the possible structures of esters with 4 carbons. Okay, so here are some esters that have 4 carbons, and in fact these are the only esters that I can think of. There might be one other, but if I look at these 4, I've got methyl propanoate, which is the blue one in the top left. I've got ethyl ethanoate, which is the one on the top right. I have propyl methanoate, bottom left, and I have, it's often called isopropyl methanoate, bottom right. Now this one bottom right can't be because it's actually only got 3 carbon environments, so we can eliminate that one to start with. But then we have to figure out, of the other 3, which one actually is it? Now, I will say right now, if you stop at this point and you say it's got to be one of these 3, then you will get a merit. Okay? No problem. As long as you've got a bit of explanation in there. But if you want the excellence, it requires a bit more work. So, what do we need to know? Well, we need to go back to the mass spectrum. And the mass spectrum has this big tall peak at 43. And so whatever structure that we want, I have to be able to get a chunk of that molecule with a mass of 43. Okay, and that's where it gets a little bit tricky. But actually, because 43, and again, on your reference sheet, it does have some information about this, 43 is a really common fragment that you can make in quite a lot of ways, which is slightly more challenging for this particular molecule. So, what could we do? Well, we could have something with 3 carbons and 7 hydrogens. Or we could have something with 2 carbons and 3 hydrogens and an oxygen, both of which could be or have a mass of 43. So if we go back to here for a sec, this bit on the left hand side of the ethyl ethanoate, so CH3 C double bond O, that's got a mass of 43. So ethyl ethanoate is definitely a possibility. If we look at the bottom left hand one, the bit that's in red here, CH2 CH2 CH3, also has a mass of 43. So that one is a possibility. But if I have a look at the top left-hand one, actually that's not a possibility, because if I break through the middle of the ester, the same place where you would do a hydrolysis reaction, actually the masses don't work. 36, 52, 53, 55, it's about 57. Then is there's no 43 peak. I cannot make a peak with a mass of 43 or a fragment with a mass of 43 from that molecule. So it can't be that one. So now I'm down to two possibilities, ethyl ethanoate or propyl methanoate. So now it really comes down, this is where you really have to engage your brain. So if we go back to propyl methanoate, the most common place that esters will fragment is in the same place that they will hydrolyze, so between the carbonyl-carbon and the oxygen. And if it fragmented there, then the HCO fragment has a mass of 29, and the OCH2CH2CH3 fragment has a mass of 59. So really, if it was this option on the bottom left, I would expect to see strong peaks at 29 and 59 in my mass spectrum. Now I do have a peak at 29 here, but there's nothing at all, not even the hint of a peak at 59. So my personal take on this is that it is unlikely to be propyl methanoate. So the most likely option is ethyl ethanoate. Now for excellence, what I'm looking for is this degree of thinking, and then for you to actually write this down. And you can just write it out exactly as I have talked it through. Okay, these are the information that I've got from the spectra. This is what it means. These are the possible structures. It can't be this one because of that. It can't be this one because of that. The fragments show that it's most likely to be this one because. That's the sort of information that I'm looking for. The language that NZQA uses is that you have integrated the information from all three spectra to determine the correct structure. And it is that word integrate. So it means you can't just talk about the three spectra separately. You have to talk about them as a whole. So you have to talk about all of the pieces of the jigsaw puzzle and how they fit together. Okay, so if you think about it like a jigsaw puzzle, you can't just go, well, the frame shows me this, and the top left-hand corner shows me this, and the next one shows me this. You really have to talk about it, this bit and this bit and this bit all go together to show me this thing. All right, so that's what I'm really looking for excellence. On the website that I have set up, you will see an example answer for a question as well, so you can see how to write it. Okay, thanks for your time, and I'll see you in the next video.